Okay, so in this session, we will have a recap about mensuration, that is cylinder, cone, and sphere. I'll just take you to the syllabus. Like, see, if you look here, area and volume of solids, we have cylinder, cone, and sphere. I'll just highlight it here. All right, three-dimensional solids. So we have right circular cylinder, right circular cone, and sphere. You have area, that is area in terms of total surface area and curved surface area and volume, and this is in syllabus, okay, direct applications, problems including cost and cost of the material here, basically, whatever the 3D object is made up of, inner and outer volumes in the case of hollow cylinder, okay, inner and outer volume, and melting and recasting. When you recast, volume is conserved. When you convert from a cone to a sphere, or from a sphere you convert to smaller cones or smaller cylinders, whatever. So in this you need to remember that volume is conserved. Okay, so surface area will not be conserved, but volume will be conserved. And you also have combination of solids, where you combine the solids and then find the combined total surface area, or the combined surface area, combined total surface area. That is when you have, let's say, a cone mounted on a hemisphere and so on. We'll just see all these one by one. Let's start off with the cylinder. So cylinder, you basically have, what is a cylinder? It's a 3D object, and it's something, it has uniform circular cross section. Yeah, like if you stack a lot of 1 rupee coins, one on top of the other, you get a cylinder. So in the cross section version, you have a circle, isn't it? The radius is r, let's say the radius is r, and so in the cross section we can see r. So area of cross section will be pi r square. There are two cross sections, isn't it? The front face and the back face, you can see here. So it will be, if you consider the cross sectional areas, you'll have pi r square plus pi r square. So it will be 2 pi r square, the front and the back. All right, and here you have the height of the cylinder. Okay, we are using the word height, and we denote it by the letter H. If it's a case, it's a road roller. We don't have height, isn't it? It's the length, but they're synonymous. So what we say as length in the case of road roller will be actually the height. I'm just assuming that it's a right circular cylinder. It is stacked, or it's like kept vertical like this. That's why the word height. Otherwise, it's all right. You can even use length. So coming to the lateral surface area. Lateral means side, isn't it? Lateral, just the curved portion, the curved cylindrical portion. It's also called a CSA because cylinder is having a curved surface area, right? The curved portion. So we're not talking of the cross section here. So CSA or LSA will be 2 pi r h. So r is the radius of the cross section, h is the height. And if it is total surface area, you will be considering the two cross-sectional phases as well, two circular phases, the top and the bottom, or the front and back. So 2 pi r h plus 2 pi r square, two circles are being added. No? So usually we can, we are factorizing, just take out 2 pi r common, h plus r. So this is a compact version of that TSA. This is it, you need to remember. And again, it goes without saying that pi is 22/7. It's not that it has to be mentioned. If it is mentioned, go with whatever is given in the question. It can be 3.14 sometimes. Otherwise, by default, you can use 22/7. Somewhere there's some dimension involved with a multiple of 7 or 11, it's going to get cancelled out. So you can go with this. That's as far as LSA and TSA and concerned. And of course, remember the unit, centimeter square, meter square. You also have to keep in mind the conversion. Let's say length is in, the height is in meters and the radius is in centimeters. You should know the conversion appropriately. See, 1 meter is 100 centimeters and 1 meter square is 100 into 100, which will be 10,000 or 10 power 4 centimeters square. You need to know this in conversion. Suppose the radius is in 1 units and the height is in some other units. You need to remember this. And what is volume? Volume is pi r square h, simple as that. So r is the radius of the cross section, h is the height, And of course, pi also is explanatory. It's 22/7 or whatever is given in the question. And for volume, the units are centimeter cube. And you also need to remember 1 meter is 100 centimeters. Therefore, 1 meter cube, you're cubing it, right? So 100 cubed centimeter cube, which is nothing but 10⁶ centimeter cube. And you also need to know, in case of liter, suppose the cylinder is you holding some water, which can be measured in liters, isn't it? Liquids we measure in liters. So remember, 1 liter is 1000 centimeter cube, and if it's 1 meter cube, it is 1000 liters. You just have to know the interconversion in these cases. So this is as far as a cylinder is concerned. Now, what if it's a hollow cylinder? Something like a ring you can visualize. So I'll just draw it like this. See, I'm just drawing a rough sketch, and always, whatever be the question, draw rough sketches. And please do draw them. It might be a word statement, a word problem, but as far as mensuration is concerned, geometry is concerned, it's always good to draw because we get clarity. It's like we are able to visualize the problem at hand. See, so this is a hollow cylinder, and actually, okay, this is the common axis, I would say. It's like you have in cross section, you have two concentric circles, isn't it? So let us say the outer radius or the radius of the outer cylinder is r, and the radius of the inner cylinder is small r. In cross section, it will be something like this. See, this is r, and this outer radius will be capital R. I'm just instead of saying R1, R2, I can say small r and capital R. What is the thickness of this wall? This hollow cylindrical wall, it is r minus r, isn't it? Outer radius minus inner radius, the thickness. So when it comes to area of the cross section, so cross section, it's like you can visualize it as a pipe or whatever pipe. Yeah, it has some substantial thickness. We can't ignore the thickness. If you're ignoring the thickness, then we'll not have the small r, capital R. It's just 1 r, right? But we are considering the thickness. Now, if you see the hollow cylinder, in the cross section, I told you, it's two concentric circles, right? So if I'm going to consider the just this portion, the area between the two circles, I could say, then the area of the cross section will be pi r square, outer circle minus inner circle. We can keep it inside r square minus r square. And very often, see, I'm seeing a difference of two squares. You can use that a square minus b square is a plus b into a minus b. You can go with this. Okay. Now, and then see, you have CSA, right? When it comes to CSA, again, remember, there is an external CSA and an internal CSA. That is just the curved portions area. I'm not talking of the cross section now. So the outer radius is capital R, right? So what will be the CSA? CSA outer, I could say. CSA outer will be 2 pi capital R into H. H is the same for both inner and outer. And when it comes to the inner radius, it is small r. So the inner CSA will be 2 pi RH, small RH. So if I'm considering the TSA, total surface area, so remember, I'm going to add up all the surface areas, whatever surface appears to me, whatever I can see is right. So hidden surface areas, leave it, but what I can see will be what? So I can see an outer surface, CSA outer, I can see an inner surface area, curved surface area inner, and I can see two concentric circles, isn't it? Two of them. So that will be what? CSA outer will be 2 pi RH. The inner surface area will be 2 pi small RH, and two concentric circles. So I'm going to add them. 2 pi, we already seen this, no? R square minus R square. So somewhat like if you look here, 2 pi is sort of common. You can just take it out. And this is, of course, this is your factorization part where you have to, if you want to simplify things and take out, if you're given a hollow cylinder, this is it. Okay. Now, this you need to remember. If it's just CSA outer, CSA inner, and so on. This is as far as your hollow cylinder is concerned. You can get problems on solving this. They can ask you to find out the H. They can ask you to find the R or the width of the hollow cylinder or the outer radius or inner radius. Okay, so again, you can use all of this. Just draw a rough sketch so you understand whether it's a solid cylinder or a hollow cylinder. Then what is asked? Is it LSA or CSA or TSA? And then is it volume? And accordingly, you can go ahead with this. And just be careful if you have multiple units, like radius is in 1 unit in centimeters, the height is in meters, and you need to know the appropriate conversion from 1 unit to the other. Okay, so this is as far as our cylinder is concerned. Just be careful with all the formulae here. So you might have questions like, there's a cylindrical vessel or a beaker or something, and then you drop an object, and initially the level of water is something, and then after dropping this object, there's a rise in the level of water, isn't it? So the volume of water that has been displaced is equal to the volume of the body that is submerged, whatever object you have dropped inside, right? That much volume of water is displaced, and hence the consequent rise in the level of water. See, now here, the solid can be anything, isn't it? It can be a sphere, it can be a cuboid or a cube. You just have to know a few things. These things you already know it. If you remember it last year, if it's a cube, if you're playing die is an example for cube, right? The 6 phases. So surface area, that is when I say TSA of the cube is total surface area 6a square, where a refers to each is the length of each edge. The length and the breadth and the height are the same, isn't it? All the 6 phases are identical, 6a square. And if it is volume, it will be a into a, which is a cube. And if it's a cuboid, obviously you'll be given the 3 dimensions, length into breadth into height. So length, breadth, and height, or even length or width or thickness, like breadth and width, and then height and thickness, they're all synonymous. So remember, the volume will be just you multiply the 3 dimensions, and of course centimeter cube or meter cube. And if it's a TSA, it will be LB plus BH plus twice of LB plus BH plus HL. So you have two identical opposite phases, isn't it? 2LB, 2BH, and 2HL. So this you need to remember. And just in case they ask you that the cuboid is dropped inside and this volume of water is displaced, or so on. Okay. All right. Now we just we'll take up problems a little later. We'll just go on to cone. I'm done with cylinder, right? I'll just go to cone. Wait. All right. So I'll just take you back to cylinder now. Just imagine I have this solid cylinder. So the base radius, or in other words, the radius of the cross section is R. And just a minute. See, the radius of the cross section is R. The height is H. Okay. So what is the volume? Pi R square H. All right. And suppose I'm drawing this here just so that it's aligned the same height. Let's say I have a cone. Okay. So a cone, now cone is this 3D object. Okay. So it's something like you have your right angle triangle, right? If I'm going to take any one of the legs that is a non-hypotenuse sides as the axis and I'm going to rotate, you can imagine, right? I'm going to get a solid like this. That's my cone. If it's hollow, you can think of your joker's cap. That is an example something they can relate to. Then you have an ice cream cone and all this, right? When you invert it, it becomes a cone. Okay, whatever. So here the cross section is not uniform, and like a cylinder, you can see, isn't it? So here you have one circle, smaller circle, and this circle keeps tapering, narrowing down, smaller and smaller circles as we go up. This peak is called as the apex of the cone, this topmost portion. This base is there, right? This cone's, this broadest circle that can find at the base. This is the base of the cone. This is the apex. So the radius of the base will be, let's say, R. Okay. So as we go up, you can see in cross section, you can find smaller and smaller circles. They're gradually decreasing as we go towards the apex or away from the base. And this height height, this is the concept of height mean there are two things that I need to remember. From the apex, I consider a line, imaginary line joining the apex to the center of the base. Base is of course a circle, isn't it? Cross section is a circle. The circle has a center. Take that center. From the apex, you can, so apex being a point and the center of the circle being a point, join the two of them. Think of an imaginary line. So you get this distance, right? This vertical distance is the h, or the height. Radius of the base is again circle, right? In cross section, it's r. Remember, it is r. All right. So, so we can imagine and that we have your h height, h, and the radius r like this. We are perpendicular. So what about this? This is also height, right? But it's a slant height. When I just mentioned the word height, it's like understood by default, it's understood to be this vertical height, h, or the vertical height, h. I don't really go about saying every time vertical height, but it's kind of understood. And L is the slant height, you can see. And in 2 dimension, they're related by this formula, h, r, and L. L becomes the hypotenuse of the slant height. So h square plus r square is equal to L square. Okay, h square plus r square is equal to L square. So you can have this Pythagorean triplets are there, right? So we have seen this 3, 4, 5. So in each of these triplets, the largest one corresponds to the hypotenuse and the other two ones correspond to the legs. 7, 24, 25, then 5, 12, 13, 8, 15, 17, 9, 40, 41. And then any triangle, right angle triangle, a triangle with the ratio sides and this ratio will necessarily have to be a right angle triangle. So obeying the Pythagoras theorem, isn't it? The sides are the ratio of the triplets. Then 11, 60, 61, 12, 35, 37, 16, 63, 65, 20, 21, 29. This is, it's not like exhaustive. There are many, many more to go. But like, as far as this chapter is concerned, I think this is good. You can, if you are familiar with these triplets, it's enough. So let's say I give you the base radius as 12, okay, and the height is 35. Height means h. Then automatically, using a triplets, we can infer that the slant height is 37. I can immediately say that, right? Because the triplets, because they have a relationship, a triplet relationship. H square plus r square is L square. So now beginning, I drew a cylinder here. Why did I do that? Now you see, let's go back to that. So see, now when I have a cylinder of height h and base radius, that is radius of cross section as r, and I consider a right circular cone, so with height h, again height I told you, it's like it refers to the distance between or the length of the line segment joining the apex to the center of the base. Base is a circle, right? And then you have the radius r here, base radius, and of course length, the slant height is L. So when you have a cylinder and a cone of the same base radius and height, what is volume of cylinder? Pi r square h. Volume of cone will be simply 1/3 of pi r square. It's very simple. Whatever it is, it will be 1/3 of the cylinder's volume for the same base radius and for the same height. It's like, in other words, the volume of 3 cones will be equal to the volume of 1 cylinder, something like this. Like if the capacity of this cylinder is, let's say, 900 cubic centimeters, I'm just giving just one example, then empirically we have found out that the volume of this cone will be 300 centimeter cube. It will be 1/3. As in, the capacity of 3 cones with the same base radius and height will be equal to the capacity of the cylinder. And coming to the CSA, just the curved part of the cylinder, CSA will be what? CSA or LSA, lateral surface area. Because it's curved, we can use the word CSA. It will be pi r into L. So you need to remember, suppose h and r are given, then for CSA you need L. So use the Pythagorean relationship. H square plus r square is L square. So if you know your triplets, you can easily get the right answer. And suppose they happen to be in the ratio of the triplets, it's very easily found out, right? Otherwise, you'll have to use your square root tables and find out and all these things. So, okay, so CSA is pi r L. And what is the TSA? So that is, I consider that, suppose it's a solid cone, then the base will be also considered, right? The bottom solid circular portion also will be considered. So along with CSA, I have to add that circular region. CSA is pi RL, and down there's one circle, right? In cylinder you have two, here you have only one. The other one is a point, apex is a point, right? So it will be pi r square. So you can take out pi r and you can take out L plus r common. So this is as far as your cone is concerned. Pi r L into pi r L into L plus r. Again, if it's if it's a hollow cone, then I mean there's nothing like base radius. There's not base radius. I mean to say there's nothing like you need not find out the TSA or total surface area or something like that. Here it's a hollow cone, and let's say they want to fill it with ice cream or something, and they'll ask you the volume of ice cream that can be accommodated in this cone or so on. So you need to remember this. So moving on, we are done with cone, CSA, TSA, and volume. There is one question here. I'll just take you to the specimen paper. Just remember it now. See here, if you see, where's that? Yeah, I just happened to just go through this, and while I was just organizing this material for mensuration, see, you can go with this specimen question paper, which says, you can see its question, right? The volume of a right circular cone with the same base radius, okay, r, and same height as that of a right circular cylinder is 120 centimeter cube. So what are they saying? You have a cone. What are they given? They're given the volume of a right circular cone with the same base radius and height as that of a right circular cylinder is 120. The volume of the cone is 120. So volume of the cylinder will be naturally 3 times more. It will be 360. So you don't need the height or radius or anything. It's just that you understand it's 3 times more. So 12 3 is 123 is 360. Okay, just remember this. So this is a one marker, and there is no big calculation involved here. Just multiply it with 3. Okay, let's go back to this. We are done with cylinder and cone, and go back to your syllabus. So yes, it's here, mensuration. Yeah. We don't have anything like hollow cone, so don't worry. Hollow cone in the sense like 2 concentric cones, and that is right now not there. So don't worry. You can have hollow cylinder, but it's like a ring. Now we move on to the sphere. So it's the most symmetrical 3D object. It's a ball. Is an example of a sphere. So radius, isn't it? So if you're going to consider in space a center point, let's say O, and in space in 3D, you consider all the points which are equidistant from a given point. Okay. So that collection of all the points is what is your sphere. So in 2D version, we say circle, 3D version of that is your sphere. So there's nothing like CSA or TSA. We just use the word surface area, but it's like TSA. It's understood to be TSA, but you're not cutting the sphere right now. No, you're considering the entire sphere. There's nothing like LSA or CSA, lateral or curved, nothing. Everything is curved itself. The CSA or TSA in this case will be 4 pi r square. Again, they found this empirically. So you can, you don't have to prove anything. Just make a note of it. The CSA or the TSA of the surface area, I would just say, let me not just confuse myself. They will say surface area of the sphere. So it will be 4 pi r square. Volume, again, empirically they have found the relationship. Volume is 4 by 3 pi r cube. 4 by 3 pi r cube. TSA is 4 pi r square. Volume is 4 by 3 pi r cube. Just be mindful of the units accordingly. One more thing that I remembered is sometimes like it will be cylinder or cone or whatever we have been seeing. Sometimes they'll give you the cross section diameter or the base radius or the base diameter they'll give. Just be careful if they suppose they say for example for the cone, if they say the base diameter is 10 centimeters, for example. So r is not 10. The diameter will be 10. So the r will be 5. So just be careful, because all your formula, TSA, CSA, all these are expressed in terms of radius. So accordingly, first extract your radius, then it becomes easy. In case they mention diameter, that's one thing. We very blindly, students, sometimes it can happen to anyone. They just take the diameter only as the radius, and the calculation will be twice of what is actually expected. So just be careful of this. So volume is done, right? TSA is 4 pi r square and the volume is 4 by 3 pi r cube for a sphere. So moving on, if it's a hemisphere, now, you know, the Earth equator is like, you know, the dividing line, right? So if it comes to hemisphere, so hemisphere, you'll have half of a sphere. So naturally, volume of sphere is 4 by 3 pi r cube. For volume of for half of 4 is 2. So 2 by 3 pi r cube will be the volume of the hemisphere. And coming to the CSA will be for the entire circle, the sphere, it will be not circle, sorry, sphere, it will be 4 pi r square. So CSA means only half the sphere is considered, it will be 2 pi r square. That is CSA. But if I'm going to consider, like say, let's say I'm going to cut a watermelon, for example. When I cut it, I'm going to get a top base, right? That is the top circular part, I'm saying. This circular part, cross section will be circular. So this will be what? Radius will be same r. R will be the radius. And this will be pi r square. The top, I'll not use the word base. It will be top circular cross section A. So it will be pi r square. So TSA of the hemisphere will be, for the hemisphere, you have to take the CSA, that curved surface area, plus the top circular face, pi r square. So it will be, CSA will be 2 pi r square, CSA part, plus pi r square, which is the top circle. Totally, when you add, you will get 3 pi r square, which is the total surface area of a hemisphere. So this you need to keep in mind. Okay. Okay, and see here, if you come down, I'm just going to the specimen paper. The inner circumference of the rim of a circular metallic tub is 44 centimeters. So they've given the inner circumference. So, all right. So they're asking you to find the inner radius of the tub, the volume of the material of the tub if its outer radius is 8 centimeters. It's obvious here, see, outer radius is 8 centimeters. Find the inner radius. For the inner radius, we can take it from the circumference itself. Inner circumference is what? Inner 2 pi r, right? If I'm assuming the inner radius to be r, small r, I'm saying. So 44 that's given is equal to 2 into 22 by 7. Makes sense to use 22 by 7 here because 44 is a multiple of 22, isn't it? And r is the inner radius, I can say. 22s are 44, 44 ones are, 44 ones are. So 7 is equal to r, or r is equal to 7 centimeters. So radius, the inner radius is 7 centimeters. The volume of the material of the tub if its outer radius is 8 centimeters. So outer radius is 8 centimeters, right? So inner radius I found out, it is 7 centimeters. So the material of the tub. Now in this case again, see, it's a hollow hemisphere. So the same thing how we apply to a cylinder. All right, but see, you will have to find the inner curved surface area plus outer curved surface area plus one concentric circle has to be added, that is pi into r minus r. So CSA inner, that is inner, I'm not right, see, it's better to write CSA. See here, the inner curved surface area plus the outer curved surface area plus this ring, concentric ring, right? Pi into r square minus r square. Now it's right. So, so CSA inner will be what? It is given already, no? That is 44 centimeters. And what is the outer? Outer one is 2 pi capital R. Capital R is 8. They've given the outer radius as 8. Yeah. So, wait. It is CSA, right? So 2 pi r square we'll take it as. Because for a CSA of a That is surface area of a sphere, it is 4 pi r square, right? So CSA outer will be 2 pi r square. CSA inner will be again 2 pi, but small r square. And you have to add that circular cross section. So this will be 44. Inner one is 44. Inner one, and that not this. The inner one is 44. It's given in the question. And then CSA outer will be 2 pi r square. So outer one will be 8, right? 8 centimeters. 2 pi r square plus, this is not circumference. We don't need 2 pi small r square. That is just now found that, isn't it? 2 pi small r square. That is inner radius plus pi into r square minus r square. That is 8 square minus 7 square. 2 pi r square plus 2 pi 8 square plus 2 pi 7 square plus pi into outer circle minus inner circle. So you can take out maybe pi common. 2 into 8 square plus 2 into 7 square plus 8 square minus 7 square. 8 plus 7 into 8 minus 7. And of course, you can simplify this. They have said use pi is 22 by 7. See, give your answer correct to 3 significant figures. So you have to forget the zeros, but if zeros come in between the numbers, you can consider them. So you'll be able to solve for this. Up to 3 significant figures, they have said. Yeah, this is how you will attack the problem. Okay. But they've asked the volume. That is, if they asked curved surface area, if they've asked volume, volume will be what? Volume, see, in volume, you need to, it's like you have to consider the volume of the material, right? This is what I found out is not asked, but I've just gone a step ahead and just mentioned all this. That is the outer curved surface area, inner curved surface area, and CSA, if they were asked the CSA. But in this question, that was not asked. What is the volume? So volume is 2/3 pi r cube minus 2/3 pi small r cube. That is the outer, what you say, outer hemisphere. You can actually visualize this as a coconut shell. If you cut open a coconut shell, you can find this, right? Something like a, approximately, you can take it like a hollow sphere. So 2/3 pi outer cube minus 2/3 pi inner cube. So this is the actual, this formula will actually give you the volume of the material inside. Now remember, for this I've used r cube minus r cube, right? See, I'll just write it down here. So when they ask you the volume of the material, you have this outer volume minus inner volume, right? Outer radius is capital R, and then inner radius will be small r. So volume is 2/3 pi r cube minus 2/3 pi small r cube. You can take out 2/3 pi r cube minus r cube. So 2/3, because for the entire sphere it is 4/3, right? This is hemisphere. All right. So we can find out this. Plus remember, you are going to consider see, in this case, it's not just that. Yeah. Because it's like you're going to consider them. It's like 2 hemispheres, outer hemisphere minus inner hemisphere. You're subtracting that so that you get the volume of the material, the thickness of the material when they ask you, because that will be associated with cost. You have to multiply it with, they will say like so many centimeter cube of the material costs so many rupees and whatever, and so accordingly you have to multiply the volume. That's, we will see a sum later. Now here it is 2 by 3 pi into r cube minus r cube. A cube minus b cube is a minus b into a square plus b square plus ab. Yeah, this is for the volume of the material. When they ask, if they ask you the TSA, this is the formula that you will be using. Curved surface area inner, curved surface area outer, and the concentric ring. In cylinder, what you used to do? Outer CSA, inner CSA, and 2 concentric rings. Here we have only one. It's a hemisphere. Okay, I think till here it should be fine, the work explanation. And then, yes, coming to the other type of problems, I told you that when you convert from one solid to the other, let's say you have a cone, you're converting the cone to, you're converting this in even, usually they won't mention that any amount is lost or wasted material. We assume that the entire cone material is available. So let's say I'm going to melt and this molten mass is recasted into, let's say, smaller, some n number of smaller spherical balls. So I don't know how many. So it's n usually. Here we need the count. We need to remember that in the volume of the cone will be equal to the volume of n spheres. N such spheres. That you need to remember. I mean, maybe they'll ask you to find n, or they might give you n and they'll ask you to find the radius of the sphere. The different types of way, different types of problems, how we can reword it. So if, for the cone, let's say the radius will be given, and if the height is given, so volume of the cone is 1/3 pi r square h, isn't it? So this cone with is melted and recasted into smaller hemispheres. N into volume of one sphere. Let us say, just for simplicity, I will say RS is the radius of the sphere, of each small sphere. So n times 4 by 3 pi RS cube. So the volume of n spheres is equal to the volume of the main cone, the mother cone from which you got the you got all of them recasted. So this is about conversion of solids. Or why should it be like this? Maybe the cone itself is recasted into the sphere itself is recasted into n smaller cones. That is also possible. Yeah, n into. So accordingly, you can use the formula. See, volume is conserved here, remember. And that's why you don't have to substitute for pi. Sometimes when they're given the question, because pi is going to get cancelled out. If you have on either side, see LHS and RHS, you can see here. So there's no need to substitute. Until the end, don't need to cancel out anything, because finally you keep on cancelling out things and finally you'll get what you want. So don't multiply it separately on the LHS or RHS, because on either side, you're going to get a lot of things, factors, common factors, and which will be cancelled. It will simplify the computation process. Now, you can also have like, a sphere, or you can say a cylinder being converted into n smaller cones or n smaller spheres. So there are different ways of rewording. So volume is conserved, not surface area. And when it comes to combination of solids, let's say I have a structure like this, some toy like this. There's a hemisphere and there's a common radius. See, you can see the cone and the hemisphere share the same radius. Yeah. And then there's the height of the cone here. And then in this case, the volume of this combined solid will be volume 1 plus volume 2. But surface area, you can't add like that, remember. So when I say volume of the cone, it is what? It is 1/3 pi r square h. And the volume of the hemisphere is what? Volume of the hemisphere is 2 by 3 pi r cube. So 1/3 pi r square h plus 2 by 3 pi r cube. They share the same radius, right? You can see here. So then you can get the combined or the volume of the combination, volume 1 plus volume 2. In surface area, it's not like that. So in this case, it will be CSA. So when I talk about surface area, CSA of the cone, curved surface area of the cone, plus it would be curved surface area of the hemisphere. Okay, you need to remember this. CSA of the cone plus CSA of the hemisphere. Because see, when I talk about surface area, it is the area. You see, curved surface means only the curved part. Or when I say surface area also, if I just say surface area also, it's understood what is visible to me. So when I'm going to look at this combination, and when I see, what do I see? I see a cone. Okay, the surface area of the cone, the outer surface area. There's no TSA concept here. I'm not talking of the base of the cone at all here. And then what I see, this hemisphere, it's curved surface area. So that's all. That is what we need to remember. Just going back to the syllabus, I'll just go back to the syllabus here. Yeah, melting, combination of solids. So that we need to remember. Then there was a sum when yesterday's I just discussed this. One of the students had this doubt. See, you have a cylinder. The bottom is raised like this. It's a hemisphere. Okay, so which means it will be like this. So if I'm just going to draw the 2D version, so you'll have the structure like this. So in 2D, it's like this. And if you're going to fill it with some water up to some level, if not the whole thing up to some level, it will be like this. See, so you can see here water will occupy all of this, and here it's empty. It's like the water will take only this shape, rather, I would say. So you can have problems where they'll ask you the level of the water, radius of this base. So the base is not flat. It's like bulged inwards, I would say. It's like a hemisphere, isn't it? It's raised. And therefore, it's like in 2D, you can imagine. It's like in 2D, it's like you have a cylinder. It's like you have an open hollow cylinder, and that hollow cylinder is placed on like a hemisphere, something like that. Okay, like this hemispherical bowl, something like that. So you can't have water here. Water can only go here, you can see. So if it's, see this portion, I'm just redrawing here, this yellow portion, there nothing, it's hollow, right? I mean, not hollow, there is air or nothing is there, nothing can be filled there, it's a block there, this one. So the water will take that shape that I have shown. Okay, so in that case, the surface area will be what? Because if you're talking about the surface area, then it will be the surface area of the cylinder plus the surface area of the hemisphere, combined surface area, it's inward. But when it comes to volume, you have to consider the volume of the cylindrical portion minus the hemisphere, because that hemisphere, it's not flat. It's not that the cylinder is flat like this. No, it's bulged inwards, right? But the hemisphere portion has to be removed from this volume to calculate the effective volume, because that much water cannot enter there in that region. Okay, that is one example. So whenever you have problems of this type, just be careful. You need to know what is the surface that is visible to me, what I can touch and feel. That surface area I need to calculate. Or you can have something like this. See, so let's say I'm going to have a cylindrical portion, and then I'm going to have a cone which is inserted onto the top of the cylinder like this. So down it is covered, top it is open, but I have a cone of the same radius. In this case, the surface area will be what? Surface area is the outer surface area of the cylinder, okay, plus cylindrical base, which is pi r square, plus, because it is going inwards, right? You have to consider this surface area also, plus CSA of the cone, which is pi r L. Okay, so that you need to remember, the CSA of the combination. So when I look at that solid, I have to look at all the surfaces that I can see, I can feel and touch. That outer surface area of all those surfaces, curved or whatever, I need to consider. That is what we mean by combination of solids. So I think this should be enough for today's session.